All right, 5.6. This is determining concavity of functions over their domains. So if we look at the function f of x equals 1 over x minus 1, I have a vertical asymptote at x equals 1. And concavity, graphically, a graph is concave up if it has a cup or U shape. And a graph is concave down when that cup is upside down or the U is upside down. There's another way to also think of this, is that if you were to draw tangent lines, if you were to do little tangent lines and you were drawing them, for concave down, the tangent lines are above it in those locations. And if it's concave up, the little tangent lines are below the graph. Does that make sense? Okay, so on this graph, f of x is concave down from negative infinity to positive 1. So it's concave down this entire time, and then it's concave up from 1 to infinity. So I can think of it in at least two different ways, and then we're going to get to the calculus part of it. So here's the definition of concavity. Let f be differentiable on an open interval I. The graph of f is concave upward on I. Now be careful, this is if f prime is increasing on the interval. So if I want f prime increasing, do you understand that that's a derivative of the derivative? And so we're going to talk about it in the green box in a moment. And it's concave downward on I if f prime is decreasing on the interval. So here's the test for concavity. Let f be a function whose second derivative exists on an open interval from a to b. Then, if f double prime of x is greater than 0 for all x in that interval, then the graph of f is concave upward. If f double prime of x is less than 0, then the graph is concave down. A point of inflection, and we're going to use POI for point of inflection, is an ordered pair where the graph changes concavity. To find a point of inflection, it's where the second derivative is 0 or it's not differentiable at x is c. But c has to be in the domain of f, okay? That does have to be there. All right, so let's go ahead and just get to work here. So the big idea is, let's kind of restate this. F of x is concave up where f double prime of x is greater than 0. F of x is concave down where f double prime of x is less than 0. X equals c is a point of inflection where f of x changes concavity. So in a nutshell, that's what we just defined. Not super precise, but just the real basics. So in example 1, it says determine the open intervals on which each graph is concave up or concave down and state any points of inflection. Justify your answer. So I'm going to give you a head start, and I want you to find the second derivative, and I want you to find where the second derivative equals 0. Then I want you to find a sign chart for the second derivative. Find where it's positive, where it's negative. plan today is to get through the 5.6 notes. Then you have a 5, 6, 5, 7 worksheet that you're going to have a few nights to work on it. So get as much of the 5, 6 content done. Then tomorrow we're going to do the partner quiz. And I haven't quite determined if I'm going to have you do an ed puzzle for 5-7 or do the 5-7 on Thursday. I'll kind of decide that later today. All right, here we go. So I'm going to find the first derivative. And then I'm going to go on to the second derivative. Now, can you tell there's no location where the second derivative is undefined? It's a polynomial. So I'm going to set that equal to 0. So then I'm getting x is 0 and x is 2. Right now, these are my possible points of inflection. I don't know until I do that sign chart. So I don't want to call them points of inflection yet. So now you can understand the method to my madness when I've told you when you're doing your sign charts to label them. Because you're going to have, when we get done, we're going to then do problems where we do everything with them. And so you need an F prime sign chart and an F double prime sign chart. So you have to label them in order to justify what you're saying. So I'm going to put 0 and I'm going to put 2. Then you're just testing. So, and I like to use my factored location. Those are easiest to determine signs, I think. So if I plug in 3, I'd have 12 times 3, 3 minus 2. That's positive. Let's say I plug in 1. That's positive times a negative. And then let's do a negative. That's a negative times a negative, which is positive. So I do a lot of abbreviating, and this would be acceptable. I'm going to say it's concave up from negative infinity to 0, union 2 to infinity. And on concavity, I do use a parenthesis because those locations are points of inflections. That's where it's changing concavity. And I'm going to say, here's your justification. Because f double prime of x is greater than 0 on those intervals. I'm going to say concave down from 0 to 2 because f double prime of x is less than 0 on that interval. Now let's talk about the points of inflection. At x is 0, does the second derivative change signs? Yes, so x equals 0 is going to be the x coordinate of the point of inflection. And at 2, is that going to be a point of inflection? Yes. So what we're going to go do, though, is let's go find f of 0 and f of 2. So that's 0. And when I do 2, that's 2 to the 4th minus 4 times 2 cubed. So then I'm going to say f of x has points of inflection, and you can use POI, at 0, 0, and 2, negative 16, because f double prime of x changes signs at x equals 0 and x equals 2. So do you see how I'm justifying and explaining? Trying to be super, super clear. Questions on letter A? What can I clarify for you? All right, then let me give you a head start on letter B. You are trying to determine concavity and points of inflection. So start with the second derivative. Set the second derivative equal to 0, or find where it might be undefined. Now that I have a fraction, I might want to pause and think about domain of f of x. Do your sign chart, and then you can determine points of inflection. Do you notice that the domain is all real numbers? Okay, because I have x squared plus 3. If it had been x squared minus 3, I'd have a problem. Okay, I would have a restriction on that domain. I'm going to go ahead and get started and pause, but I want to make sure that you were able to find the second derivative correctly. So I'm going to bring down the power, decrease the power by 1, and then apply the chain rule. So that's negative 12x times x squared plus 3 to the negative 2 power. Then I'm going to do the second derivative, which requires the product rule. So I'm going to take the first times the derivative of the second. So I bring down the negative 2, decrease the power by 1, and the chain rule, plus the second times the derivative of the first. So what is that? 48x squared times x squared plus 3 to the negative 3 minus 12x times x squared plus 3 to the negative 2. Yeah. Oh. Yes, thank you. Yeah. Pull that puppy up there. Thank you. Yes, because the derivative of negative 12x is just negative 12. So then I am wanting to set this equal to 0. And let's see if you can stay with me here. If I factor out the 12 out of the 48 and the 12, but then when I have x squared plus 3 to the negative 3 and x squared plus 3 to the negative 2, I want to pull out the greatest common factor, and that's actually going to be to the negative third power, okay? So then that's going to give me what? 4x squared minus the quantity x squared plus 3. Okay, so let me pause here because this is oftentimes an area where students get confused with the algebra that's happening. So look, if I had pulled out the negative 2, then I would have had x squared plus 3 to the negative 1, and that would still be yucky. So I want to pull out that smaller exponent, the negative 3, because now that's just to the first 4x squared. And then here, you understand that if that's to the first power, and I'm taking like a to the m times a to the n, I would add the exponent. So that really is equivalent to x squared plus 3 to the negative 2. All right, so now watch what I'm going to do. This will be 12, and then do you see that's 4x squared minus x squared minus 3. So that's 12 times 3x squared minus 3. Then do you see I can actually factor out the 3? This is the problem that will not end. And you know, I do have weird things that pop in my head. Here's a weird thing. Do you know from SpongeBob? This is the song that never ends. It goes on and on, my friend. Okay, so this is x equals plus or minus 1. The denominator is not ever equal to 0, so it's not undefined. So x equals 1, x equals minus 1 are possible points of inflection. So I'm going to pause again. And let you do your number line chart. That second derivative was tough. Okay, that was a tough second derivative. All right, I'm going to go ahead and start my sign chart. So I'm going to label it f double prime of x. All right, so if I plug in 2, that's 36 times 2 plus 1, 2 minus 1. And do you understand that that denominator is always going to be positive? Okay, so I could sort of like just ignore it as I'm doing this. So that's going to be positive. Then let's choose 0. So that's a minus. And again, I can just start ignoring the denominator because it's always positive. And then let's do 36 negative 2 plus 1, negative 2 minus 1. So that is positive. So here we go. We're going to say concave up from negative infinity to negative 1. And you can use the union or the and is okay. Because f double prime of x is greater than 0 on those intervals. Concave down from negative 1 to 1 because f double prime is less than 0 on that interval. How do you determine a point of inflection? Good job. Okay, a point of inflection occurs where the second derivative changes signs. So x equals negative 1 and x equals 1 are going to be locations of points of inflection. So let's go figure out f of 1 and f of negative 1. Can you tell they're going to be the same because that's x squared? So that's 6/4. All right, and here's how I'm going to justify that. I'm going to say f of x has points of inflections at 1, 3/2 and negative 1, 3/2 because f double prime of x changes signs at x equals 1 and x equals negative 1. Yeah, David?
Could you explain a little more why for APC we usually use closed intervals and for what comes in temperature, open as we use
the open? Yeah, that's a great question. So remember we talked yesterday about the formal definition of increasing is so every point beside it, it's going to be higher and higher. So that's why we included it. In concavity, our definition is on an open interval. That's the difference. Okay, that is the, and like I mentioned before though, like if it's really bugging you on the increasing, make them open. It's okay. They're not going to mark it wrong. Right. What other questions? Okay, then let's try letter C. I'm going to give you a head start again. I strongly recommend you consider your domain. and I hope you can appreciate the extra time we spent on finding first and second derivatives and using quotient rule, chain rule, because I knew what was coming, and I wanted us to really build solid math belts for ourselves to increase your success later in the course. All right, I'm going to go ahead and do the second derivative just to make sure you got there okay. Before I begin, though, I'm going to just mention my domain. X is going to be all real numbers except 2 and negative 2. So I'm going to keep that in the back of my mind as I'm working through this. So you're going to do low d high minus high d low over low low. Before you go to do your second derivative, tidy that up. Yeah.
So why did you, in the problem before, did you use the product rule and move stuff negative?
Okay, in letter C, I could do that as well. However, in letter B, do you see the numerator was a constant, and so I didn't have to do the product rule for the first derivative. That's why. Great question, though. Great question. So let me tidy this first derivative up and get 2x cubed minus 8x minus 2x cubed minus 2x. So that's negative 10x over x squared minus 4 squared. So I can make my life a whole lot easier if I, tidy that up. Now I can do my second derivative. So this will be low d high minus high d low. So I'm going to have to do the power rule with the chain rule. So I bring down the power, decrease the power by 1, and take the derivative of the inside. Now when I do low low, what exponent will that be? 4. Good. All right, so eventually I'm going to set this equal to 0. So let's go negative 10 x squared minus 4 squared. Then I have a negative negative, so that's a plus. So I'm getting 40x squared. And, whoa, okay, let me try and keep this straight. Then that'll be a minus. Is that 160? Yeah, yeah, let's do that. Okay, and what about a 10? Yeah, let's factor out the negative 10 and an x squared minus 4. Let's do that, because I'm like, whoa. So then that'll leave me with an x squared minus 4 to the first. Then I took one of those negatives out, but I have another negative left. And then that would be what, 4x squared? Because I took a 10 out, right? I'm getting lost in my own work here. Because I pulled the 10, right? Yeah, no, I'm good. Okay. Over the x squared minus 4 to the fourth. Then one of those, so I'm going to get, what, negative 3x squared minus 4. Yep, oh, beautiful. And then I can cancel one of the x squared minus 4s with this one. Okay, I'm going to cancel one of those. And then x squared minus 4x squared is the negative 3x squared, and I got minus 4. Then let me go ahead and factor out a negative. All right, so there we go. So f double prime of x never is equal to 0 because the numerator is always positive. Let me say that again. 3x squared plus 4 is never going to equal 0. F double prime of x is undefined at x is plus or minus 2. Now I know that it's not a point of inflection because x can't be plus or minus 2. However, what I do know, and this is where your pre-calculus foundation is going to come in when you did all that rational graphing, okay? So if I look back at the original f of x, what is happening graphically at x is 2 and negative 2? Asymptotes, okay? Vertical asymptotes. So I can still determine concavity. Okay, it doesn't mean that it's not concave up or concave down. So let me go ahead and do my sign chart. And this is why we say that x is 2 and x is negative 2 are possible points of inflection. I know they end up not being points of inflection, but they break up the graph somehow. Okay, there's some sort of a change occurring there. And I'm going to go into that further. So let's say the number 3. So what I would have is 3 squared plus 1 over 3 squared minus 4. That numerator is always positive, so I really don't care about that. But then that's a positive over a positive. Let's say I do 0. That would be 1 over negative 4. Oh, sorry. I don't know. I'm a nut. I'm an absolute nut. I don't know. Thank you. No, I went f double prime. So here we go. But still, my numerator is still positive everywhere. So that's 3 times 3 squared plus 4 over 3 squared minus 4 cubed. So that was positive. Sorry about that. No, I want to definitely plug into f double prime of x. Then let's suppose we plug in the 0. And do you see that's negative? Then go ahead and try the third one. What I mentioned yesterday and previously is that do not assume that the intervals alternate. They do not always alternate. A lot of times they do, but they do not always. So in this case it did. This was a plus. So this is concave up from negative infinity to negative 2, union 2 to infinity, because f double prime of x is positive. on those intervals, concave down from -2 to 2, because f double prime of x is negative on that interval. So here's where, and this problem was intentional. So it looks like, according to our sign chart, that 2 and -2 are points of inflection. But they're not, because if you look at our tippy top, x equals 2 and -2 are not part of our domain. So we need to say that there are no points of inflection because f of x, not f double prime of x, is because f of x is not defined at x equals ±2. Now down below, I have graphed all three of these, A, B, and C. So if you'll take a look at, let's look at the third one here. Do you see this is in fact concave up from -infinity to -2. It's concave up again from 2 to infinity. And it's concave down between -2 and 2, and there's no points of inflection. And what I want to point out to you is, if you're a little bit confused about it, do you remember what I mentioned? If you could draw little tangent lines, when it's concave up, the little tangent lines are underneath your graph. And when it's concave down, the little tangent lines are above it. So then let's look at letter B's graph. And what I want you to notice, this is like really, really cool. Do you see it's concave up, concave up, concave up? But then there's a place where it's now concave down, the little tangent lines go above it. And then there's a spot where it switches. Does that make sense? Can you see it? Where we had in letter B, it was concave up, and then let me see what our point was again. I think it was at 1 and -1. You see, then it's changing here and here. It's changing that concavity. All right, so your homework tonight, you are not going to be submitting anything yet. You're going to pull up the 5, 6, 5, 7 worksheet and get started on the problems from 5, 6. Tomorrow is the partner quiz, 5, 1 to 5, 5.